Howdy, y'all. We're going to do some midterm review. So I'm going to start with chapter 1, which was our first unit of the year. And my goal in this video is to just go over the highlights and the key points of chapter 1. So here goes. In section 1.1, we learned about analyzing categorical variables. Actually, let me take a step back. In the intro, just the introduction to this unit, we talked about categorical variables and quantitative variables, and being able to identify is a categorical quantitative or categorical, and then the group of individuals, whether it be people or animals or things, that's who we collect data about. We take a human, we measure their arm span, that's quantitative. We measure their hair color, that's categorical, etc., etc. And a distribution of the variable just goes through all of the different outcomes and how often those outcomes occur. So then we got into section 1.1. And in section 1.1, we analyzed categorical variables. And categorical variables are going to lead to a percent. So we looked at things like frequency tables, relative frequency tables. So I'm going to just use the textbook to give examples here. This is a frequency table. What kind of radio station music do you listen to? And relative, the word relative means percentage, converting from a frequency to a percentage. So that's the difference between frequency and relative frequency. And then we looked at ways to display categorical variables. You have bar graphs and you have pie charts. So displays for categorical variables. Bar graph, and I'm going to put in parentheses as we got later on in this unit, maybe in this section, side-by-side bar graphs we did, and segmented, and I'll get more into those in a bit, and pie charts or pie graphs. And we talked about really the AP part of the curriculum is not pie graphs, so you're not going to see those very, very much at all. Well, you're not going to see them at all. So bar graphs, couple things. When you have a bar graph, label axes. We've kind of jokingly talked about, like, if you don't label your axes, like, you're not dateable. Like, yeah, all jokes aside, like, I don't want you to lose credit on your exam. Make sure you label your axes. You need to have gaps between the bars. Okay, so this is a bar graph. All right. Let's see. Oh, bad graphs. So what are some bad graphs? So there's a couple of good examples here. You don't want to ever use picture graphs because they're misleading. And the other thing you don't ever want to do is you want to make sure you always start your y-axis at 0. I don't see an example specifically in the book right now that I can show you, but you always want to start at 0 on the y-axis. Okay. Then we moved into two-way tables and marginal distributions. Two-way tables and marginal distributions. So two-way tables show you the relationship between two categorical variables, in this case, gender and opinion about what the likelihood is that they're going to get rich. Okay, so that's what a two-way table will display. Then we talked about a marginal distribution. Marginal, the keyword for a marginal distribution is the totals. It's the distribution of the totals. Marginal means totals. So for us in this example, if I wanted the marginal distribution of gender, it would be this 23 divided by this 48 and the 24 divided by the 48. Obviously the whole numbers, I'm just abbreviating. If I wanted the marginal distribution of opinion, I would take each of these total opinions divided by the 4,826. Those would be marginal distributions. Okay. Then we moved on to, okay, what happens if we look at a conditional distribution? So the difference is here when we have a conditional distribution, this is based on a given. And what do I mean by that? So let me show you this table again. So I might only be looking at the females or only be looking at the males. So here, the reason marginal distributions aren't fantastic is they tell us nothing about the relationship between the two variables. So when we want to start talking, is there an association between gender and opinion? We have to look at the conditional distribution. So if I want the conditional distribution of opinion among women, I am only looking at this part of the table. I'm only looking at the females. And then as you see here, I'm dividing each of the opinions by the total number of females. Conditional distribution means you're not using the table total. You're not going to use this 4,826. And then what this is going to do is this will allow us to start comparing to see if there's an association between, in this case, gender and opinion. Okay, the definition's a little clunky. I'm not a huge fan of it. So this now calculates the conditional distribution of opinion among the young men. So now we're looking just for the males, and you can see we're dividing each of the opinions by the total amount of males. So then what I can do is I can compare male to female and start to see, is there a difference between the males and the females who think they have almost no chance of being rich, some chance, etc., etc. And that will lead you to being able to tell, is there an association between the two? Okay, so here you can see the opinion, male and female. Now this is a different conditional distribution, and it's a segmented bar graph. So what they did is almost none. So they took the 96 divided by the 194 for the female and 98 divided by the 194 for male. We're just looking at that row. And you'll see that the male percentage is slightly higher. They did the same thing for some chance. 428 divided by 712, 286 divided by 712. So the percentage for female here is higher. And they did this for each of the three. So then we started talking about, is opinion and gender, are they associated or are they not associated? And what we talked about is the idea, if there is an association, that means knowing the value of one variable helps us make a prediction about the value of the other variable. So for example, if I know someone's opinion is they have some chance of being rich, now I know they're probably more likely to be female. So these variables are associated. If there was no association, then all of these bars would be the exact same percentages, whether it's 80% female, 20% male, or 50-50, or some other breakdown. All right, another way that I'm going to show this to you is going back to the conditional distribution of gender, so female, male. What they've done here is a side-by-side bar graph, which I kind of like a little bit better. It's easier to do the comparisons. So they looked at the different opinions, almost none, and then they compared the female to the male. Those are about the same. Some chance, you can see females are a lot more likely to believe they have some chance. And then the other 50-50 is about the same. And then for good and almost certain, males have a higher likelihood to believe that. If these variables were independent, each of these pairs of bars would be the same. So these would be the same. These would be the same. It might be like 15%. These are around 30. Okay, the percentages can fluctuate from category to category, but male to female would be the same for every single one. Because then if I know some specific opinion, 50-50, I don't have any more information on if the person's male or female because they're both 30% likely to say they have a 50-50 chance. So to summarize here, if you're asked if there's an association, you're going to have to compare conditional distributions using either a side-by-side bar graph or a segmented bar graph. And you're going to have to label, you're going to have to show your work, all that stuff that goes into that. But that's how you would determine if there was an association or not. All right, so let me just show you this. I like this. Here's an example of a segmented bar graph where there is no association, because you can see this is 4%, approximately this may be like 15% for the greens, and the yellows are the same percentage, the reds and the purples. So if I know somebody has a 50-50 chance, I don't know anything. I don't know that they're more likely to be female or male. I don't know anything. They look exactly the same. All right. So quick summary, relative means percentage. Pie graphs and bar graphs are how we display categorical variables. Once we get into a two-way table, that shows the relationship between two categorical variables. And then we can analyze those two-way tables looking at marginal distributions, which are the totals, or conditional distributions, which will help us answer the question, is there an association between these two variables? And we can use a side-by-side or segmented bar graph to answer that. So that's the first section, section 1.1. That was pretty in-depth. Oh my goodness. Section 1.2. Now we just got into displaying quantitative data. So now if we're measuring something that has units, there's a few different ways we can do this. So if we're measuring quantitative data in section 1.2, I'm just going to abbreviate quant data. This is where we're talking about making a dot plot. I don't want to get too far ahead. Histogram and stem plot is what we did in this section. Dot plot, histograms, and stem plots. So we've made a bunch of dot plots. That should be pretty comfortable. Anytime you're talking about a distribution, hey, guess what? We're going to talk about CVS, which we've been talking about all the time. Center, variability, spread. So you want to make sure you discuss those. You discuss those in context. So then for like shape, we talked about describing the shape. Is it roughly symmetric? Is it skewed to the right? Is it skewed to the left? We talked about, is it unimodal? Is it bimodal? Does it have a couple of peaks? Is it uniform? Okay, so for shape, we have roughly symmetric. We have uniform. Uniform is it's approximately all the same height. We have skewed right, tails on the right, skewed left, tails on the left. Yeah, whether it's a dot plot, a stem plot, a histogram, all of that is the same. Now, then we got into comparing distributions. And I'm losing sight of what acronym I actually told you earlier in the year. But you have to compare. Did I give you SOX? I've taught so many different ones over the years. I can't remember which one I did. COS. Visco, VSCO. I think that's the one I taught you. All right, I had to go through that. You're going to compare variability, you're going to compare shape, you're going to compare center, and you're going to compare if there's any gaps or outliers. But you have to use comparative words. So when I'm looking at these two distributions, household size in South Africa and the UK, I'm going to stay away from numbers here, but I have to use these comparative words, greater than, less than, about the same. So the shape of household size is different in that in South Africa it's unimodal and skewed to the right, where in the UK it's unimodal and roughly symmetric. They're different in shape. Center. The center household size is higher in South Africa than in the UK. Okay, I could give specific numbers, but I'm just comparing. There is more variability in household size in South Africa than the UK. More variability. Outliers. The UK does not appear to have any outliers. In South Africa, there's potential outlier at 15 and 26, with a gap from 13 to 15 and 15 to 26. So I'm just writing a statement for each of those 4 prompts via CO. Make sure you have context in there at least once. All right, how to make a stem plot. When you're doing a stem plot, a couple things you want to make sure that you have. You want to find the min and the max. Use all stems between and have a key. So I'm just going to take some, let's say some test scores, 81, 96, 64, 85, 92, 98. Min, 64, max, 98. So I'm splitting these numbers. So when I think about stem 6, there are no numbers in the 7s, no scores in the 70s, but I still need that 7, 8, 9. Leaf 4, that's gone. Nothing in the 70s, 81, 85, 92, 96, 98. And I want to make sure each number takes up about the same amount of space because I need to kind of consider this like a dot plot so then when I start thinking about shape and things like that. Okay, I need a key. So 6/4 equals a 64 for their test score. So I know what that actually represents. All right, so that's what I want to think about when I'm making a stem plot. You could have back-to-back stem plots. So they're going to go from the smallest number towards the center to the biggest out. And then you have to compare these stem plots. This gets difficult as far as like the shape goes. So let me just show you here. The shape of this, I'm going from least to greatest. The tail would be on the right if I draw a curve over this. This would be unimodal and skewed right. When I go about it the other way, though, I can't look from left to right because I'm going greatest to least. So I got to think least to greatest. There'd be more of a tail on the left. But I got to think about flipping this over so that 0 is on the left and 5 is on the right. So this would still be skewed to the right. If you have specific data, which you do, like 0, 4 represents 4, 2/2 is 22, I could plug this data into a list, 4, 5, 5, 5, 6, 7, 7, 7, and calculate one variable statistics to get like the mean, the median, the standard deviation, all that stuff. Okay, histograms, benefit is you can just put a whole bunch of data into a histogram. So they have these things called classes or bins. So here, everything 0 up to but not including 5 gets dumped into this one. Everything from 5 up to and not including 10 gets dumped into this one. What we want to avoid is using frequency. We want to use relative frequency. It just makes it a lot easier to compare. Like here, this is 20, this is 40. I don't want to compare those because those are different frequencies. It's not going to be that simple to compare those. All right, what else we got here? How to do a histogram on the calculator. You can read through that. I'm not going to go through that. Using histograms wisely. Oh, this is a good one. Histogram, bar graph. Whoa, they look pretty similar. Are they the same? No. Histogram has no gaps between the bars, and it has labels on both axes, and it's a quantitative variable. Bar graph has gaps between the bars, label the axes, but this is a categorical variable. All right, so summarizing. There's 3 different types of plots we can use for quantitative variables: dot plot, stem plot, histogram. And then when you have one of those, you want to be able to describe it using VSCO, variability, shape, center, outliers. And then as far as the shape goes, is it unimodal, bimodal, multimodal, symmetric, skewed left, skewed right, uniform? So quick summary of section 1-2. Let's move on to section 1-3, which was the end of chapter 1. I don't know why I'm doing that with my voice, but it's fun. Okay. So section 1.3, we went a little deeper on the quantitative variables here. We actually calculated measures of center, mean and median, calculated and interpreted measures of spread, the range, the IQR, and the standard deviation. And then we had to pick when should we use mean, when should we use median, and when should we use like IQR or standard deviation. We talked about outliers, how to calculate those. We talked about box plots, how to actually do those. So let's do this. So section 1.3. We did measures of center are the mean and the median. And measures of variability or spread is the range, which is just your max minus your min, your standard deviation, and your IQR, which is quartile 3 minus quartile 1. So what we have is, we started talking about resistant. Which of these is resistant? Which is not resistant? If we have a big outlier, that's going to influence the mean. That's not going to influence the median. Really quick example. If I have this, the mean is 2, the median is 2. If I add the number 10,000 to this, the mean is much, much, much bigger, and the median's 2.5. So the mean is not resistant to skewness and outliers, and the median is resistant. It may not change at all. It may change slightly. The range is not resistant. The standard deviation, because that's the average distance from the mean, it includes the mean. This is also not resistant. The IQR is resistant. It's the 75th percentile minus the 25th percentile. And I'm picking my nose on camera. That's great. Okay, well, I'm a human being. Oh, well. Okay, finding the median, when the median is odd, comparing the mean and median. All right, so does this get into the skewness? Yeah, it does. All right, so for the skewness, if I have a distribution that's skewed to the right, the mean is going to be pulled up by these larger values. So if you have a distribution that's skewed right, then the mean is greater than the median. If you have a distribution that is skewed to the left, the mean is pulled down by those values. So skewed to the left, the mean is less than the median. All right. And if you have a distribution that's roughly symmetric, the mean and the median are pretty much the same. Oh, let's see. Okay. Okay. So then we got into box plots and rules for outliers. To determine if something is an outlier, you're going to have a value that's an outlier if the value is greater than the third quartile plus 1.5 times the IQR, or the value is less than quartile 1 minus 1.5 times the IQR. That's how you determine if something is an outlier or not. So when we start getting into box plots here, what they're going to do is they're going to give you a 5-number summary. And the 5-number summary for the box plot is the min, the median, the max, quartile 1, and quartile 3. So here's an example. Here's the 5-number summary, the min, quartile 1, median, quartile 3, max. What they had to do was check to see if there was any outliers first. The lower value was negative 3.75 when you use that formula. There was no data below that. The upper fence, as I think I may have called it, was 74.25. No values went beyond that. So there's no outliers. What if there are outliers? Well, you do something like this. You use a little asterisk to represent any outlier. There could be 2 or 3. And then you stop your box plot at the next highest or lowest value that's not an outlier. So outliers are going to be denoted by little asterisks or little circles. One thing to be really, really careful with when you're talking about box plots and you're talking about their shape. The shape, we can't tell if it's roughly symmetric, but we cannot say it's approximately normal. We can't say if it's unimodal, bimodal. So when you're talking about a box plot, never talk about it being approximately normal or anything about the mode. That's kind of what that's saying here. How to do box plots on the calculator, that's important. Make sure you know how to do that. Then we got into standard deviation. Standard deviation is simply the typical distance from the mean, average distance from the mean. Okay. Talked talked about that. Interpreting it, yeah. All right. Moving along. Okay. All right. Yeah, that's pretty much it. So, summary. We just kind of dug deeper on center, shape, and variability. Not on shape, center or variability. Center, you have two ways to measure it, mean and median. The quartiles, a couple different ways you can measure your variability. You can measure it using IQR, standard deviation, or range. We hardly ever use range. Variance. This is something that came up later on in the year. The standard deviation squared is the variance. So that's still a measure of variability. We talked about being resistant. And then, yeah, there's one thing I didn't really cover that I want to go back and cover. All right. So if you do have a skewed distribution, for your measure, let me just start on the next page, actually. If your distribution is skewed, then the measure of center you want to use is the median, because that's resistant. And the measure of variability you want to use is the IQR, because that is resistant. If you have a roughly symmetric distribution, whether it's uniform or approximately normal, the measure of center you want to use is the mean. The reason is that takes into account every single data point, and the measure